Welcome back. This is Psychology Applied to Work, Lecture 5, Analysis in IO Psychology. Okay, remember last lecture we talked about the science of IO Psychology. This is the second half of Chapter 2, Analysis. In the science of IO Psychology, we talked about the scientific method, and hopefully a lot of this was a review for you. And we discussed a little bit about maturity and complexity of the various domains of science with the provocative question, is psychology mature enough to be a predictive science? We talked about variables, independent variable, dependent variables, control and experimental groups. And we talked about the replication or the reproducibility crisis, where poor statistical rigor and techniques that weren't quite as good, weren't quite as scientific as was thought at the time, resulted in findings that turned out not to replicate, and then how the domain of psychology has taken this very seriously and approaches statistical rigor as one of its core principles now. And we talked about experimental methods, and specifically we talked about correlations, causation, and confounding variables. We talked about negative and positive correlations, that sort of thing. And we talked about observations, naturalistic observations, in the wild, so to speak, out at the workplace, and then artificial settings for observations. And then we finished our lecture on surveys. So today, for the second half of Chapter 2, Analysis, we're going to talk about descriptive statistics, and that's will be just in a second. And we're going to talk about distributions. We're going to talk about inferential statistics and meta-analysis, and we're going to end with just some examples of workplace variables. Now, those terms, descriptive statistic, inferential statistics, meta-analysis, if those aren't familiar to you, don't worry. The concepts are actually pretty basic, and this should actually be a pretty straightforward lecture. Okay, descriptive statistics. What are descriptive statistics? Well, oftentimes the raw data that you have from your observation or your experiment can be complex, and you need to try to find the signal from the noise, try to find the pattern, try to pull the meaning out. And descriptive statistics are a way that you take data and make them more concise, find dimensions within the data in which you can use to describe what's happening in a meaningful way. So you're summarizing features of the data. One of the most common ways of doing that is graphically, and that can be like a bar graph, or it could be distribution curves, which we'll talk about here. So like a frequency distribution can be plotted. And there's an example on this slide of what's called the normal distribution. If you haven't, if this is all new to you, we'll explain it. If this is all review for you, by all means, turn up the speed on this video to the level that suits you. So a frequency is really how often this something happens. So each one of the occurrences or the count would be the y-axis on that curve, and then what the corresponding variable to that count would be on the x-axis. So you could maybe look at it of the height of women in Norway, and that might be a distribution of that, where the x-axis represents various heights, and the y-axis, the y-axis represents various number of people, like what percent of people or total count of people, and then the x-axis could represent heights from short to tall, and you would end up with a curve that looks somewhat like that. And so this is a useful way to see, to get meaningful information, see the patterns in the data. And then descriptive statistics like this give you a way to find what's called the central tendencies of the data. And the main things that are looked for is what it's called mean, median, and modes. And this is probably familiar at some level. You've probably run into this a few times. This might be, something backwards and forwards, or it might be one of those. Yeah, what are those again? Don't worry if you can't rattle off mean, median, and mode in terms of what the differences are. It's just one of those things when you're using it every day, you remember, and if you don't, you kind of have to go look it up again. No big deal, and we'll go through what they are in a little bit. You can also look at how much variability there is in the data. In the case of that graph on this slide, the amount of variability is manifest in the shape of that curve. So the more it's broad, like a flat mound, the more variable it is, and the more it narrows to like a tall sharp point, or like a skyscraper where the ends come in. The less variability that is, in the standard way in which that's expressed is something called the standard deviation, and we're not going to go through the math, or the math's not hard. But the standard deviation tells you about the measure the variability, and so in the case of certain types of curves, what are called a normal curve, or a Gaussian, or a bell curve, and we'll talk about more of that in a second. But you can do standard deviations will tell you like what percentage of the data falls within a certain range, and so you can see that the 68, the 95, and the 99, and the 99.98 are all the 1, 2, 3, and 4 standard deviation values. Okay, let's talk about distributions in a little more detail here. And again, this is an introductory IO psychology class. The field of psychology. If you want to get a degree in psychology, you'll go through a lot of statistics, and it's very important. And this class is just sort of a high-level introduction. So we're not going to be going into detail, but what is important is that you understand some of the broad pattern, the impact of this information, why proper statistical rigor is so essential, how poor statistics can be misleading, and then just some basics of things like the different types of distributions, which is where we are right now. Okay, let's look at that the two curves on the top. So the first curve on the left, the two on the top, it would be like a histogram. So you've got your bars, and those would represent individual. Those things could be like height, and then of women in Norway, and then on the y-axis would be how many. You grabbed surveyed 1,000 women at a big sporting event in Norway, and the y-axis could be just the count, and then the x-axis could be the height. The people in Scandinavia are pretty tall, so your center height would probably be higher than it would be in Southern Europe, for instance. And then on the right is a smoothed out version of that curve, where you don't see the individual units, but it shows just a pattern of the data. In this case, that's what's called a normal distribution, which is a symmetric about the mean and the mode and the median. In this case, the mean, the mode, and the median are the exact same spot, and we'll explain that here as we go. So this is called a bell curve. The central tendencies all align in a symmetric distribution like this. But you can also have what are called skewed distributions, which are the two on the bottom, and the histogram on the left, and then just sort of the pattern behind that histogram on the right. And there you see the mean, the mode, and the median are in different locations. So obviously it's asymmetrical. In a skewed distribution, when you're trying to get, what is the central tendency, the median is actually a stronger central tendency, stronger. It's more meaningful usually for what the data is telling you. because the mean itself can be a little bit misleading, and hopefully that'll make sense as we go. So what are these mean, mode, and medians? So the mean is just the average. Okay, that's probably the mean is probably the most used of all the central tendencies, and it's the easiest to sort of intuit when you're looking at when you're talking about averages and the average height, and the average height of here are the average heights of women in Norway, and it's a curve. You'd think if I said the average height is 5'9", they're tall. I don't know what the average height of women in Norway is, but I'm going to Google it after this because I should know this if I'm going to bring it up. But I didn't know I was going to bring it up. Anyway, mean is just the average. The median is actually the midpoint value. So that if you had 1,000 Norwegian women that you found at the sporting event, what's the point in which 500 of them are taller than your point, and 500 of them are shorter, or well, that'd be 1,001, but you understand what I mean. So the median is really where that center point of that information is, and then the mode is really what's the most occurring value. What's the height that had the highest number of Norwegian women? And so when you have a normal distribution, it should be clear now why the average and the midpoint value, the median, and the most occurring all happen on the same height in this example. So bell curves, Gaussians, normal distributions, all the same thing. Central tendencies are all the same, but in something like a skewed distribution, in this case, like you can have left skewed, you can have right skewed. There, the central tendencies are different, and so you can see the graph in the form of a skew, but then you can get the central tendency data, and all of those things give you a sense of what this information is telling you. And this is just high level overview, and we're not going to dive into it. But you should know that there's way more to life than a Gaussian. Okay, there's way more to life than a normal distribution or a slightly skewed normal distribution. There are things like bimodal, trimodal. I mean, you can have all sorts of noise in your distribution that's coming from various things. If you're surveying 1,000 Norwegian women, when you only had maybe 20 of them, you wouldn't have had a nice, beautiful normal distribution. It would be messy and representative of low statistical power, which is to say too small of a sample size, so that too much is due to just randomness. But you could have a phenomenon that has a complex distribution when you try to map it out, and that would tell you that, hey, there's a lot going on here, and then so your central tendency information wouldn't be very useful. You can also have fat-tailed distribution. So imagine that skewed distribution, but sort of stretch that tail out, and you don't have a fat tail is a general term for where you have that flattened part of the distribution, but that it stretches out fairly long, and so at any given point along that tail, you don't have a lot of occurrences. So there aren't a lot of Norwegian women that have a certain height at any given point. But if that tail's long enough, and you add them all up, that can say things like there's a tremendous amount of variability, or the number that are really, really tall or the number that are really, really short is actually quite large. Fat tails come into play in statistics for things like unforeseen events, pandemics and wars. If you made a plot of on what's the chance of a pandemic or a major war in any given year, you would for the most part show that the chance is extremely low in any given year, but the chance is not zero, and if you go year after year after year, eventually that you're gonna hit that, I'm not describing how you do that graphically, but that's the power of long tail distributions. Anyway, the important thing to remember here is what a normal distribution is, what a skewed distribution is, and that these are like idealized versions of data And oftentimes life is a lot messier than this. Okay, inferential statistics. What are inferential statistics? So you can think of this as inference, and you can think of an inference is a probabilistic estimate, and so this is a way of looking at your data in terms of probabilities, in terms of likelihoods. Whereas when you were looking at a normal distribution, that's what actually happened. Those are the heights of the 1,000 women at the Scandinavian sporting event that you measured. But another way of looking at data is in terms of probability and statistical significance, which is to say, okay, I see this data. How can I do my analysis that says that this is not due to randomness? And that's where like coming in, when you're, again, measuring heights of Norwegian women, if you only have 20 of them, you're going to be subject to chance. I mean, you could end up believing that the average height is way lower or way higher. And so how do you look at the pattern of your data and determine how much of this is signal, so to speak, and how much of this is noise? And that's where inferential statistics come in. And a big part of that is what's called the p-value, and the p-value is really the probability. And in this case, it's the probability that this event was due to chance. So there's a lot of math I'm not sharing involved in analysis, where you're looking at the patterns of data to say does the pattern have a lot of noise in it or not, and then trying to pull something like a p-value out of your data. The important thing to remember is that it's basically a measure that's critical, and you're trying to figure out whether the experiment that you did that showed a difference between your experimental group and your control group, how do I know that that didn't happen by chance? Or at least how can I have as much confidence as I can that it didn't happen by chance? So it's really what you're looking at with the p-value is that difference. And it's common that you're using the means there, the averages between the experimental group and the control group. And so if you have a p, or a probability of 0.1, that's a 10% chance. So you did some manipulation to your independent variable and exposed your experimental group to that manipulation, and you looked at your dependent variable, and when you manipulated your independent variable in one direction, you saw a direction in the dependent variable, and you're saying, hey, there's a really high correlation, and you're excited about it because you've shown that playing Neil Diamond music increased the productivity of teams. You wouldn't have seen that necessarily with every single group, and you might not have seen that every time. So you can look at what variation you do have, and some other things that we won't get into, and you can determine what your p-value is. So if you came with a p-value of 1, that's like okay, that's a 90% chance that what you saw was real, that it's a real effect, that maybe people do perform better at teams when they listen to Neil Diamond music. And if you don't know who Neil Diamond is, that's fine. Billie Eilish, how about that? But 1 in 10, that's actually not that good, especially when you're talking about trying to make a claim, when you're trying to advance the domain of psychology or whatever your field is. 10% is not very good, and you want to do better than that. And so, a general threshold, and this sort of depends on domains and other stuff. But generally speaking, the threshold that there's a strange consensus around is 0.05, which is to say there's a 5% chance, looking at the data, that this could be just chance, or 1 in 20, which is to say if you repeated this 20 times, well, you get the idea. Now you want to have a better than 0.05, and so having something like a p-value of 0.01, which says there's a 1% chance, and sometimes you'll see a p-value of 0.001, or even better than that, a 0.001 would be 1 in 1,000 that this is by chance. So this part's really critical, that you look at what your data is, and you become confident through statistical rigor of what your odds that this is by chance. And you have to publish this. So, and even if you had a p-value of 0.01, it still means that, you know, at least the way this thing is framed, a 1% chance of this data could be garbage. That this correlation that you see might not be repeatable, and that's actually why you still try to replicate things, even when you get good p-values. So hopefully this makes sense. So we talked about p-hacking a little bit, and this would be just a good reminder. So you know, going through your data, if you have if you're tracking multiple variables, sometimes you can just, you know, maybe you track 10 different variables. So you played Billie Eilish, and you also turned the blinds down, and you got more comfortable seats, and you did whatever. And you got groups together alphabetically, or you just paid attention to birth dates of who was on the team, and you just lined up all sorts of data. And then you got your results, and say that, you know, a certain number of teams did better than other teams. And then you p-hack, which is to say you look at your relationships, and then you determine that teams that have team leaders with birthdays in August perform way better, because it just so happens that two of the best teams happen to have leaders selected that had birthdays in August. And what came out of that is a good p-value, which is to say, hey, according to the p-value, this wasn't by chance. And that's actually not the right way to look at it. That's not correct. The p-value tells you there's always a chance. You can't look at a p-value of 0.01 and say it couldn't have happened by chance. So I mean, let's look at a p-value of 0.05, you know, 1 in 20, 5% chance. Well, if you were actually tracking 10 different variables, the probability that you might find a good correlation between one of those 10 and the outcome you were looking at, you know, you're essentially after the fact sort of redefining what's an independent and a dependent variable when you're p-hacking. So you try to see what's going on. And there's a lot of stuff that got published, effects that were claimed, and people got really excited about some of them. And it turned out it was p-hacking. And no, p-hacking doesn't mean that you did some sort of voodoo magic and for sure this couldn't have happened. You know, it's you know, who knows, maybe there's something about people who have birthdays in August. That was just something I grabbed randomly. But that's why you do replications, and that's why p-hacking is frowned upon. If you stumble on it, I mean, you're just looking at your data after your experiments and you see something and you're effectively p-hacking, that's not something you want to put a paper on. But that is something that tells you, maybe there's something to this. Now let's try to replicate this. Now let's try to actually let's put a bunch of teams together, and we're going to make the independent variable the birth date of the team leaders. And then what you probably find, because your initial results were from p-hacking, you'll probably find that this thing goes away, and it was just the luck of the draw. So anyway, hopefully you follow this okay. So we looked at this graphic last lecture, and I wanted to bring it back up again because we're going to dig a little bit into this for this lecture some more. So recall that the top line is positive correlations, the bottom series is negative correlations, with the correlation being the R value, and the correlation getting stronger as you're moving to the right. We're not going to get into what like an R squared is and that sort of thing, but it's not really, you'd think like you see an R value of 0.33 there on the second one from the left, and then next to it is an R value of 0.66, and you'd think, oh, that's you know, half as strong, but I mean, it's not the right way to look at it, and we're not going to get into R squared, but if you square them, that difference becomes higher. But just look at the patterning of the data, and hopefully when we're done with the next couple slides, it'll make sense to why this really matters. If you don't know who XKCD is, if you're a nerd, especially if you're sort of a STEM nerd, XKCD is a great comic strip. This brilliant stuff. So here there's a scatter plot, and somebody found the linear trend line, or did what's called linear regression, and effectively said, hey, you know, there's an actual correlation here. You know, there's a real trend in the data. And XKCD is basically saying it doesn't trust these things when it's harder to guess. So take that red trend line out of there and look at that scatter plot. I mean, would you draw it that way? If that was flat or turned the other way, would you say just as good a chance that might have been true? So the joke is that when it's harder to guess the direction than it would be to just figure out what are constellations you could draw, that maybe we shouldn't trust that. So how does that manifest sometimes in actual publications? So this publication is a correlation between performance and IQ amongst some in Denmark over several years with 1 million different people. And you look at that, and that's IQ on the x-axis, and that's an aggregate sort of measure of performance. That can mean lots of stuff, but just for the sake of this argument, we're not going to get into that. But that shows, oh, hey, if the smarter you are, the better you perform. Life is better for you if you're smart, and life isn't as good for you if you're not smart. So that's a linear regression. That's a trend line. That's a correlation. So hey, pretty compelling narrative that IQ and outcomes match. Well, that the correct way of stating it would be that IQ and outcomes have a weak correlation. And remember, correlation is not causation, but what's also important is the term weak. And weak implies that there's lots and lots of other factors at play. So perhaps one of the fiercest contemporaneous modern critics of social sciences is Nicholas Taleb. And his famous book, Black Swan, is an excellent book. All of his books, frankly, are excellent. He's a curmudgeonly fellow, doesn't suffer fools. But one should listen to your fiercest critics. And so when this was what he shared, presumably being the data behind that paper. And I'm not, picking a fight with this paper. This tendency of only plotting linear regression and not the scatter plot is pretty normal. It's pretty standard in the domain. And psychologists generally have enough of a familiarity with statistics that they know when they see a linear regression line that there is some form of a scatter plot behind it, and they know how to read the R values, and then they know how to filter through a paper to see how much confidence was in there, how much signal was there, how much noise. So the convention, that the sort of expectation within the journal is to just put the shorthand in of what the relationship was. Just put that linear line, and you see this all the time, and it's considered acceptable in the domain, and because the domain understands it, sure, that there's maybe a messy scatter plot, and we know that, and we're smart, and we see that when we look through it, but I don't want to see scatter plots when I want to quickly assess a paper. Well, people have different opinions about that. I for one, don't like it at all, and wish that this paper, for instance, would have, if they're going to put that linear regression, that line in there, they should also put it in the context of the scatter plot. And so why does that matter? Well, why does it matter if all scientists understand this? Why make it more difficult? Well, psychology doesn't live in a vacuum, and psychology isn't ignored by the press. In fact, psychology is watched very closely by the press because it studies people. Everybody at some level is a psychologist, or wants to be, or certainly has some kind of a model of what a psychological understanding of the world, or right or wrong, subtle or otherwise. So so-called findings that happen in the domain, and they make it out, and then they get shared in the media and traditional legacy media, social media, and everything else. Well, those two representations of the data, one just being linear regression and one the linear regression with the raw data behind it, they can tell dramatically different stories. So that y-axis is performance. Where is the highest performing dot? It's right about at the average IQ. Do you think that's an important little detail? As you move to the right of the y-axis, so you're talking positive x values, which is IQs higher than average. What fraction of people with an IQ higher than average actually had fairly poor performance that were below the 0 line? Quite a few. Now look at the left side of the scatter plot graph. Look at the people who had low IQs and look at how many high performers there are. This is big. This is people. So you might have a child who seems lower in IQ or average in IQ, or you yourself might be, or you may have students. And if you look at that, if you get the paper on the left, or the paper is what comes through, and you don't understand that the actual data behind it looks like that scatter plot, that will affect your view of the world. That will affect your view of your child or yourself or your student. When in fact, based upon that scatter plot, is IQ a predictor of performance? A little. Is having a very low IQ more of a disadvantage, and having a high IQ an advantage? Yeah. Is it the only thing? Nope, not by a long, long shot. And when you look at where the high performers are, and how some of the really high performers, they aren't super high IQ, that says there's lots of other factors here. And if you only tell the message of the one factor, you're misleading. And you'll see this all the time. And this shorthand of a linear regression isn't necessarily considered bad science. And I'm not calling into question the scientific rigor behind this, or whether or not authors of papers like this understood these things. I say they do. But I'm listening to the critique of people like Taleb, and that just linear regressions don't tell the full picture. They don't talk about the complexity, and the end result can be a narrative that is limiting to people's outcomes. That people said, well, I guess I'm not going to do that because I'm not smart enough. Well, if you actually looked at the scatter plot and somebody was explaining that to you, oh yeah, maybe I will. Maybe I will try this. Maybe I will major in this. Maybe I will go to college. Maybe I will go to grad school. As it turns out that things like perseverance and grit, and who your network is, and luck, lots of other things factor in to various measures of success. Okay, I'll get off my soapbox here. We're going to go into correlation, causation, reciprocality a little bit more here, and try to graphically represent it to try to help you develop an intuition for this. All right, so this example has been used by a lot of people. It's a good one. Ice cream sales cause shark attacks. Scientists say. And so how could that be? This isn't just it's a facetious example of how mistaking correlation for causation can result in absurdity. So say you're going to the beach, and it's a hot sunny day, and they sell ice cream at the beach, and you find yourself hot and in the sun on the beach and hungry, and ooh, ice cream sounds good, and you have some ice cream. Well, to some extent, of all the various things that caused you to have ice cream, and therefore to have the sales at the ice cream vendor go up, one of the things that caused you to do that is the fact that you went to the beach. So also the causes are like you're hungry and you have good associations with ice cream, and somebody asked you to get some ice cream with them, whatever. One of the causal factors was the fact that you went to the beach. Now, if you happen to find yourself getting attacked by a shark, there's a good chance you went to the beach. The shark attacks don't tend to occur while golfing or at the mall. So if you go to the beach and you go into the ocean, that is generally where shark attacks occur. So if you go to the beach and find yourself being attacked by a shark, by a shark. One of the reasons why you were attacked by a shark is because you went to the beach. But the connection between ice cream sales and shark attacks is correlation. So I mean, hopefully that is crystal clear. It's a good example. And when you want to try to think about, was this correlation, causation, what's what again, and how do I remember it? You can think about going to the beach, ice cream, and shark attacks. And it is actually it is super critical that you remember and remember again and again, because your brain will keep forgetting this when you see findings from studies. You have to remember that with correlations, even when they have a super compelling causal relationship, and you feel really, really strong that this correlation is causal. Most of these correlations are fairly weak, which is to say it's one. If it's causal, it's one of many, many, many causes. And we have we bounded rationality, and we think in terms of effective abstracted spatial narratives that dramatically limits our ability to conceptualize complexity. And we love the simple explanations, provided they feel like they're coherent. They feel like they sum up what's going on. And so there is this this temptation to want these this caused that, and you've got to remember that usually when it comes to complex things like things that happen to humans, that there are many, many, many more causes. And these things have serious life-altering consequences if you think of them too narrowly. If you don't recognize that if you see a relationship that says you and your circumstance has less of a chance of success in something because of something that appears to be science-like, or is purported to be really solid science that says the data shows that you, because of who you are less likely to get promoted into a position because look at this data that shows this clear relationship. Okay, the data might be sort of correct, but if what they're showing is a weak correlation, even if that's causal, even if because you're a certain type of person, because you're too old, or you don't have the right look, or you don't have the right gender, or whatever, that there are circumstances in which people will act in a manner that disadvantages you. That might be there might be that at play, and that might be a factor, and that if you look at the data hard enough, you might be able to tease out that weak correlation. But what if that's only one of 20 factors? What if only 1 in 20 factors is ageism? Your probability of being selected for something, that if you get older, you're less likely. If that's 1 in 20 factors. What if another factor is a person's own assessment that because they're older, they won't get selected, and therefore they opt out? What if that factor, okay, the self selecting out, the choosing not to even put your name in the hat, or your hat in the ring, or whatever, what if that factor is actually a stronger factor than the actual occurrence of ageism in these things? So think about that. And a lot of these simple narratives that get pushed out into the media with allegedly with deep scientific rigor and great statistics behind it, and they turn it into these simple causal relationships, when often there are multiple factors, and this is just one. And again, the highest performing people in that big study that we shared on the screen, that some of the highest performing people were not the people with the high IQ. And this isn't a conversation about IQ. That's just an easy one to pick. But this is about whenever you're seeing these correlations and how they can be used to basically tell a cartoon narrative that isn't representative of the complexity of life. And don't stop yourself and don't sell yourself short, because you saw some relationship or you heard something without really thinking it through. That there's probably a lot more factors, and some of those other factors you might actually be those things might actually advantage you, even if some factors might disadvantage you. So think about these things. Okay, another critical concept that hopefully I can help you get an intuition for with some graphics, and that's reciprocality, and that's circular causation is another way of looking at this. Sometimes feedback loops are sometimes a descriptive way of looking at it. So imagine that you're good looking. Okay, maybe some of you are. Okay, for all I know, all of you are. Okay, but if you happen to be good looking and you're interacting with people, generally speaking, all other variables accounted for, people have a slightly more positive reaction to good-looking people than non-good-looking people. Again, all other variables controlled for. So, if you're having all sorts of social encounters and you happen to be good-looking, your odds of your social encounters being positive are slightly higher than people that aren't as good-looking. And that means that your experiences, your social interactions are positive, more, tend to be more positive. And that might make you, pretty happy. And that might make you more friendly. And then you're now being friendlier in your social interactions. And people also like friendly people. And so here you are being friendly, and now they're more friendly to you, and they're naturally a little bit friendly to you because you're good looking, and you get this virtuous cycle. This thing that just spirals and sort of self-sustains. And so if you ever meet somebody that's just super charismatic, charming, and wonderful to be around, and also very good looking, there's a reasonable chance that could be because a lot of their experiences with humans throughout their life are more positive than other people's. Now, let's look at the flip side of that. So that's a virtuous cycle. But there's also vicious cycles, and sometimes people call them circles. But if you're playing in some sort of competition, and it could be a team sport, it could be chess, it could be whatever, you're doing something that involves some variability, and you're competing, and you lose. That actual loss puts you at a slightly increased chance of losing the next time if you don't change anything, because you have a slightly reduced confidence, because life taught you that, hey, I can lose, or maybe I'm a loser, all sorts of stuff, and that can change how you then see the world the next time around. You might not give it as much energy. You might second guess yourself, all sorts of things that can cause you to then lose again. And so losing itself can be a vicious cycle. Then winning can be a virtuous cycle. And you kind of know this stuff. Now, it's more complex than that. This is not the only thing going on. You lose, you reduce confidence, but at the same time, you get a little fearful because you don't want to, be a loser, whatever that means. And so you kick it in the butt a little bit. You actually change your behavior. And so these things aren't inevitable. They are not inevitable. Because you win and it's great and you have high confidence. The next time around, you actually don't try that hard because you're a little confident. So these things aren't singular. But if you really think about things in life, you'll run into this reciprocality all the time. So think about this graphic. There's a lot here to digest. That if you really understand it, you understand correlation and causation, and how important it is to know the distinction, and to know that you really actually can never truly get to cause when you're just looking at data. You just get more and more confident that you have something that could be causal. But kind of like truth, in science, you don't ever find it. You just keep pursuing it. And cause is actually a form of truth, so to speak. So you're trying to get closer to a higher confidence in cause. And correlation, oftentimes in social sciences, the only thing they have for a currency, so to speak, is correlations. And so be careful, drawing conclusions on the latest science, the latest thing that's coming out of the domain that the press gets a hold of. What's the scatter plot behind it, and if it's just a correlation, that doesn't mean causation. Anyway, a lot to think about here. Okay, meta-analysis, and this is pretty brief. You could have a whole course on how to do a meta-analysis properly, but just understanding it conceptually is pretty straightforward. So it's really just combining multiple studies, as long as they're done fairly similarly, to dramatically increase your sample size. It's kind of like a form of serial repeatability, where you basically, do it again to increase your sample size and to reduce the chances of that your data is due to chance. And so you're getting greater statistical power that can cut through the noise. And often meta-analysis are used when a domain can't quite make their mind up about something, because there's a series of studies that come out that all show that there is an effect between, say, two variables, and then some studies came out and say they don't see an effect, and the domain can be arguing about this for, in some cases, for years. Well, a meta-analysis is an attempt to try to look at all of them together and see if the data can say, whether the effect is real or not. But here's the deal: to do a meta-analysis, it requires a great deal of expertise, and there's lots of technical argument around how to properly do a meta-analysis. And just because you see a meta-analysis was done, that doesn't mean that that's the end. That's the end of that of the argument, because seldom, if you're looking at some study that is, say, looking at performance versus years of schooling or something, and if there are, say, 20 different studies, or in some cases when things go for years and years, you might have like 60 different studies. The chances of those 60 studies actually being identical are like nothing. So you have to develop criteria before you can actually combine studies, or you actually are not combining the same thing. And so the devil is really in the details of a meta-analysis, and a poorly made meta-analysis is not a good thing. So a bad meta-analysis is bad science, but it's kind of it's a technique that that science can use to try to sort of resolve issues that can't seem to be resolved, because studies are super hard to perform. It's hard to get enough people together, enough subjects together. And so over time, if enough researchers do enough studies, if you carefully look at the studies to see what you can combine, you can find you have a large enough sample size in the end to maybe draw something like a conclusion. Okay, we'll wrap this lecture up with just sort of a flavor of what are some of the variables that happen in the workplace. Again, this is psychology applied to work. We've spent 2 lectures now on the basic tools and techniques, the science and analysis of the data behind IO psychology. But most of what we've been talking about applies to all of psychology, and in some cases broader parts of social psychology. So you want to bring this back to the workplace, just to get you to see the sheer number of variables that could be at play. And this is absolutely just a partial list. So what are some of the variables? I mean, where you are is a variable, the culture, the work culture, but also the underlying regional, ethnic, national culture. even things like height of a desk, how big of a desk is, what shift you're doing, night shift, midnight shift, weekend shift, day shift. All of these can have additional factors that come to play. The age, specific age of a subject, the average age of an experimental group versus a control group. There's other characteristics as well that generally speaking would be diversity characteristics, but there's also there's also individual differences in personalities, health, both on the aggregate and at the subject level, and we're just going to blast through these as you see, as you just sort of look through the list. Again, just a very incomplete list. There are all sorts of things at play in the workplace that could be influencing results that you might be looking at, and we're trying to improve job performance, we're trying to increase engagement, we're trying to lower turnover, trying to keep higher retention, and you're trying to set up an observation or even an experiment. There's a lot going on, so that should give you just a taste of why this is a challenging field. But again, you're talking about real organizations that exist in the world. Some of them are nonprofit, some of them are government, some of them are educational, some of them are for-profit businesses. This is applied psychology, and the work that is done has meaning. It is impactful, and even though there's a lot of headwinds in terms of confounding variables, it is a worthy endeavor. Okay, that ends lecture 5. We finished this up a few minutes early. I went over on a couple other lectures, so I'm trying to stay right by you in terms of total time. But let's review what we talked about. So this was analysis in chapter 2, and we finished up chapter 2. We introduced descriptive statistics, and this was things like distribution curves and that sort of thing. And we went into some of the different types of distributions, and we talked about inferential statistics, and this was really about probabilities. And we talked about like p-values and p-hacking, and then we talked about meta-analysis and how to aggregate more subjects, so to speak, try to pool together multiple studies to try to get enough statistical power so you might be able to say something more conclusive about a difficult topic. And critical here is performing a meta-analysis is a complex thing, and a bad meta-analysis is bad science. And then we just got a tease for all the different variables that are at play in the workplace. Okay, next lecture is our second bonus lecture for extra credit. And here we're going to talk about groups and complexity. So in that we're going to talk about group process, and that's a term in psychology, and it's a term in IO psychology, group process research. We're going to talk about how sometimes groups of people are actually pretty smart. We're going to talk about how sometimes they're not so smart, and we're going to talk about group polarization, which is a very relevant thing, given the level of polarization right now in our broader culture. But what is group polarization? Why does it tend to happen? And then we will talk about complexity a little bit more, and we'll actually use a physics example. No math, and it's intuitive, and it's just bodies in space attracted to each other. But how when you go from 2 bodies to 3 bodies that are interacting with each other, that it becomes extraordinarily difficult to predict the outcomes over an extended period of time, and why. And hopefully, if you understand this concept, you will see how broadly this is applied to our multi-factor world, our world where there are so many different causes for phenomenon, especially with humans, and having a good intuition is really helpful, and thinking of it as a 3-body problem for me was the most helpful way that I got my sort of head around this, and I'll share that with you, and hopefully it's helpful for you. And then that whole multiple variables at play, makes things quite dynamic and makes human interactions quite chaotic, and we'll explore that in a little detail. And then we'll talk about heuristics versus that complexity. So we have bounded rationality. We have sort of evolved networks or gadgets in our brain for handling things. We like simple narratives. We like linear causal things, but the world is so much more complex than we can literally imagine. So we develop useful heuristics in the face of that complexity, and some of them are quite useful. And as long as we recognize them as heuristics, as sort of imperfect ways of viewing things and not perfect representations of the actual reality, then they can continue to be very useful for us. So, okay, that concludes lecture 5. So now we've finished up chapter 2. Hopefully you're also caught up on the reading, and next lecture is a bonus lecture that hopefully you also find interesting, and we'll see you then.